Hello. Today I actually wanted to start work in the Calculus 1 series, but I suddenly understood that I don't have any passion whatsoever for introducing real numbers, and I didn't want to just do something what I don't have any passion for, even though we need real numbers for basically all of the calculus. So this is a mandatory topic. I have to introduce him, but well, I didn't want to do it mm, while being bored by what I'm doing, and so I decided to find motivation for actually introducing real numbers for myself, and so I started thinking. Or I like to start thinking um, what actually warrants a number notion generally, because we'll start by the numbers and we'll develop all our notions based on them, we'll take them as given, and so kind of all our numbers in our structure will be structurally uh, encompassed by the real numbers. And so that was the question, what exactly makes us think of numbers, and not historically. Historically, I don't really care. I, at least um, in at the moment now, I don't really care. I could talk long time about the topic, potential and from the real perspective and whatsoever, but I would like to see kind of a mathematical warrantedness of numbers, and not some trivial, but rather um, some kind of basic mathematical structure, but not while assuming them, like looking at different objects that involve them. No, not in that way, but in a way that we consider mathematics without numbers, and look how this mathematics would somehow hint, perhaps, towards numbers. I don't know what it will become, but let's see. I just would like to motivate myself to make videos about numbers. So we are doing maths without numbers. And when I talk about maths without numbers, I mean nothing that somehow involves a concept that um, actually is equivalent to thinking of numbers, the thinking of numbers as entities abiding to certain rules is allowed. Well, maybe we'll relax it a little bit, we'll see. Maths without numbers. But what can we actually do without numbers? Okay, let's imagine humanity has never invented any numbers, but on some non-historical way, in the way of alternative history, humanity came up with uh, the mathematics that does not involve them. That is, humanity has come up with what? Yeah. Um, the first thing that comes to mind, with which mathematics pretty much began, except for numbers, is geometry. And perhaps geometry like drawing some patterns that were kind of geometric nature was even before numbers. So geometry. But geometry in kind of limited fashion, right? We could not calculate anything. We don't have numbers. We just have shapes. We certainly have shapes. There's no problem with that. And when we, for example, I don't know, draw something like that, this is allowed because it is connected to the number 3, but we could draw it just like that. Right? The problem, a problem could occur when we show that to someone and like um, ask to draw the same thing. How exactly would that person do that? Well, I mean, a similar thing. Just draw, we tell this person, well, could you draw something like this? Then the thinking that might have developed then is like this. We do not count, but we kind of say, I draw such. Then I kind of don't continue, but I draw such, and I connect. And this somehow implicit this notion of a number because I draw such and then draw such. This is kind of hinting at a number, but even without developing numbers, such thinking should be possible, right? So triangles are okay. They wouldn't be called triangles, but we call them triangles just because it's our name, so that. But you would be just considered drawing that like that. You would not, the number 3 would not be figured in any way. Alright, so shapes. Of course, also that is okay. Something with 4, but 4 would not be mentioned. Instead, for example, by way of comparison, mm, here kind of this and this and this, and here kind of this and this and this and this. So, very primitive notion of a number, simply in sense that one does some action and then does another action and then does another action and one does some action and one does another action is kind of not same, but without realizing that is allowed because we only want to drop numbers um, as something more sophisticated than just carrying out actions one after another and not counting them. So those people do not count. They just kind of have this intuitive feeling that this is kind of not same as this. All right, not same even in all in a very general sense, not same. What we could call free angle or triangle and quadrangle, four angle. Right, so we could have shapes. And now people could give them some names. Maybe we would just say that we do not like this. This would be symbol for this. Alright? Corresponding the symbol for this would be, I don't know. So now people could say, no, we can actually investigate them. For example, and this is an interesting concept. Without numbers, we could still have equality. For example, this length, uh, not length in our sense, but length in the sense of these people without numbers, is equal to this length. And so the concept of equality would be there because you could compare objects and see, well, they're kind of equal, even without numbers. So equality is independent of numbers. It might have historically developed in abstract fashion only with numbers, but we are not interested in that. We are interested just in ability to build a certain framework of reasoning. Equality independent of numbers. So we have something, we have equality. Okay, and of course also inequality. And I mean not equality, by inequality. Equality and inequality is independent of numbers. Oh, that's great. Right. Um, Also similarity of shapes. Similarity of shapes. And I don't mean that we compute some similar coefficients. That is of course prohibited. There's no such thing whatsoever. Similarity of shapes is independent of numbers. right? Similarity of shapes could be, for example, that this kind of has same form as this, and I have tried to draw it with same angles. Okay. And same angles, of course, doesn't mean that you measure the angles. It just means you draw them same, right? This is alpha. This is alpha. Okay, that's great. Equality in a very general sense, equality of objects. Independent of numbers, similarity of shapes is independent of numbers. And now, um, what could we say about triangles without numbers at all? Well, we could still, since there's equality, we could have um, equilateral triangle. That shape is allowed, right? We could have uh, like two equal sides triangle. And I don't mean two, I just mean draw this, draw this, draw this, and draw this equal, draw this equal, and draw this. So not two equal sides, but um, okay, in our language too, but let's put it just in such quotation marks because we do not really mean two. We mean just not all. And of course not triangle, but okay, I will use our terminology, but we keep in mind that there are no numbers whatsoever. Okay, you try to do most simple things. What things actually do work? Half right angle. Oh, let's, yeah, okay. Half right angle. Because right angle is a purely geometry concept. If you like, we have quantized it. Since we could have taken each number to be this, it's totally independent of numbers, clearly. We have right angle. An interesting question would be if we would have something like less or more. I'm guessing rather not in an abstract fashion. In an abstract fashion, we actually could not compare things. Probably can't make abstract comparisons. And sense of less more being generalized. But we couldn't make comparisons of sense of less more being generalized. But we could say this angle is actually inside this angle, right? And since this angle is inside, it is somehow related. And this angle is outside this angle. So comparison of angles is allowed. Also comparison of like okay, comparison of angles certainly allowed because it's just visual. But comparison of other things we have to be careful. So comparisons are allowed when they're visual or like understandable or conceivable in some other sense than using numbers. Okay, well, we have circles, so we have n angles, and we don't mean n. We don't mean n as number. We just mean such shapes. We just mean such shapes that we can draw like this. And perhaps we would also have convexity and concavity. Most likely because it looks have n angles, have circles, certain. Oh, what else do we have? We have, of course, 3D objects, just the same. 3D objects. Um, basically, have anything we can draw. And okay, of course, so I'm not mentioning it anymore. We have no numbers. Without applying numbers. To be able to draw it. Okay, we have anything we can draw, but we can't even measure sizes except for simple comparison of similar objects. Right, so actually, what do we have? Geometry. Without quantification. So geometry without quantities. Or more or less. What could we do in such geometry? Well, we certainly could have parallelity. Of lines, and then we could have those angles and whatever is those is right, and whatever else is here. I think that's it. We could have that. And we could actually probably establish equality of some triangles at least. For example, if we take something like, okay, that's probably too simple. Let's see equality of what triangles we could, in what case we could establish equality of triangles. Oh, actually, in all cases, because it is just based on equalities, so equality of triangles can be established. When it can be established without computations. So, in particular, arguments that use area of a triangle, they do not work anymore because we can't, or area of whatsoever, we can't compare areas anymore in no way. Well, okay, in particular cases we could like that, but we have no general way to compare areas, to compute areas, or to do whatever with areas. Only in very primitive case we can do it. Okay, equality of triangles can be established. So, what do we lose of geometry actually? That's the bigger question. What do we lose in geometry? I mean, concretely, what results do we lose in elementary geometry? Well, I'd like to start rather simply. So let's look at simple things. Um, and there's like a lot. So we cannot specify objects with precise measurements. Precise measurements. And by that I mean in our context precise, unless uh, shown in drawing. Okay, that is the only way how we can specify objects with, so to speak, precise measurements of exactly the object that we'd like to have. We can only draw it, there's no way. So in particular, if two people want to have same objects, then they would have to take the object of the other and would have to copy that very carefully. If you want to have the object with exactly those measurements, there's no way. Right? Copy. You would have to copy like every line in exactly that way, right? Like it was drawn. Okay. Cannot specify objects with precise measurements. What else do we lose? Of course, lose some of inner angles of a triangle. So of that thing that is drawn like this. And let's think if we can somehow save it. Is there any way to have that all triangles, because that is what it comes down to, all triangles have same sum of inner angles? Yeah, is there a sum? Yes, when it can be interpreted directly. So yeah, we have some notion of a sum, and probably we can save that for triangle because any triangle we can draw this, right? And we can draw this so that this parallel to this. Let that be called AC. That's really AC parallel BD. And we have what am I doing? So that is if we have another triangle and this is really another triangle. Then we can see this and this and this give us that no matter how we like rearrange that, so is that, and that is this and this and this put together like this is VEG. This is here put to this together EGB, put to that EGB, right, and this GB, and I do not follow the notation because I just you understand what I mean, right? And now this one AEC PEG VEG is always that one, right? And that we can notice. We can notice that even without numbers, no problem. So, but we can to some extent save if even if not quantitatively. So that is some certain calculations of some sorts we will be able to do. We can also do minus in some way. Yeah. But we see that it will be like difficult to write down because we would have to do this depict or think of that in that way of putting that together and things like that. Okay. Okay, but that is great. Next stuff that we could look at. I forgot it already again, I think. Well, could we now prove first that if those two are equal, then those two are equal? actually it is equivalent. Okay. Okay, we would have to actually have. No, we can do that. We can always, without numbers, do that. Right? Okay. So, if those two are equal, okay, we have to. Okay, we have to have something to start with. All right. Those two are equal. And then the thing that has equal distance for points. That is actually an interesting question. If we would have that, it would be orthogonal. Let's think about it. We could certainly build an orthogonal thing, right? No problem with that. Right, and if we have an angle here, and we have okay, that seems to work. If we have angles, then it certainly works because angles with those angles just give us this angle, right? Just by our sum theorem. It is not quantitative, but is always same is left if we take two angles out of here, right? So same is left here. We can compare it. It's equal, and then we have all the comparisons of equality of triangles. So we just have two angles by one side, right? And 2 and 1 are of course not given, but we kind of, in a way, can see it looks like that. All right. Okay, so angles given, and we can have that. All right. Now this given, we have angle, two sides, and we have the angle not there where it should be for us to conclude. Okay, so now we have the situation of two sides given. We can of course construct third side, and we would actually need that this third side would divide this angle and angle equal, this angle equal to this angle. But this is okay. How would you do that? Oh, if those are equal, then we would have done something like this, and we would see. Okay, I think we would have that as axiom. We'd have as axiom that this actually divides this angle into equal angles, and not two but unequal angles. We would have that as axiom, and then we would have concluded that. Alright. Alright, so we can now probably prove this. So this is axiom. Axiom about perpendicular bisector. And having numbers we can prove, of course, prove this. Assuming analogic notions. Okay, but actually in stellar geometry, I don't recall. Oh, I don't know if that is clear, right? Actually, why is that clear? Yes, because of the short angle. Yeah, yeah, yeah. Okay. Um, but this here, that if we have two equal sides, we actually have those angles equal, or those angles equal. Uh, why would that be true? I don't know. I would think that it is also axiom in standard geometry, but I'm not so sure. I mean, there is no quantitative difference, so probably, yes, I don't see at this stage of geometry what kind of theorem could be even applicable to evoke on equality of triangles, right? And equality of triangles, if we have just that and that, and we have that angle, it just doesn't work. Alright, if we have that angle, and we have that and that, then it just does not work. That's right. Hmm. Yeah, I would think for now pretty much that it is an axiom if we have two equal sides. This would divide this angle. We orthogonal thing would divide this angle into two equal angles. Right, okay. We could think about it more, or maybe not, doesn't matter. Don't have to derive everything thinking. Just want to have an impression. Alright. And now we have that equal to that. That's by the way a very interesting topic. If we would have something like equations, but let's see if we even need that. Because, well, yeah, what we would see that this angle is actually same as this and this angle, and well, that doesn't suffice yet, right? Actually, it does. I'm thinking now without numbers, so yeah. Actually, it does because you see, if we put it like that into that, then we just come up with putting it. We just come up this is same as this, and to obtain that this is same as this, we have to put this, and this is what comes out on the other side, right? Because we could put the same, and so this is same as this, and this is same as this. So we could prove this theorem. Very nice. But on using this axiom. Right. Alright, and so on, I actually claim, except for explicitly quantitative results, we can do everything. geometry without numbers. But this is just a clay. And of course, there are people working at it, there are people like looking at what remains of Euclidean geometry if you take away this thing, that thing. I think what I did here was actually, oh yeah, pretty much. I'm pretty sure that it is true because oh okay, I just put a sentence here. Geometry is study of invariants. Of yeah, actually, pretty of invariants under certain. Oh, let's call it. I don't want to call it what it is usually called. Geometry study of invariants under certain um changes describing the nature of the underlying setting. This is of course not rigorous, but if you want climbing perspective, so you have to Google Felix Klein Erlangen, and of course this version is kind of very artificial, but yeah, kind of to get like an impression without diving into what it actually is. I think it is a good description. Okay. Okay, so I'm pretty sure we can do all geometry actually. We can do everything in geometry. Well, everything is such a word. We can do everything in geometry except for explicitly quantitative results. That is what I actually claim for every non-quantitative result. There's a way to derive in geometry, of course, in Euclidean geometry. Euclidean geometry. There's a way to derive it. Non-qualitatively and non-quantitatively, that is by comparison like shown above. Even if We currently might not know such. Of course, that raises the question, how am I going to really derive that such a half circle is something like this area if I just um, using that we are in our world, just take that this is some number r, this is some, I don't know, uh, that's the right, and we have just uh, why do I need both? That's a good question. And just have I we have for this sorry, that would be we have length. I have pi d squared this, and I can just say, wow, it's pi d half squared, right? And then it has same as. Of course, you could ask me how would I derive that? The result is d half same areas. Same areas, so it is not quantitative. But in truth, area is per se quantitative. Quantitative notion. Why is that? Because comparison like this is more than this in area, which we could do at our before numbers, doesn't involve the comparison notion of the area. This notion of number comparison of areas is a artificial. It can't be done in any um, in any non-quantitative fashion. You could do it without quantitative fashion. It's intrinsic, not because it is intrinsic in this comparison phase because it is intrinsic in the area. You couldn't. There's no way to somehow assess the area of this um, in a proper way without introducing quantitative things. It is impossible. Right, so area is per se quantitative notion. Can now be length, and as I said, we compare like objects of exactly same shape in can do that. So you can do comparisons meaning ordering, right? Small or equal. Probably would not call it that, but yeah, small or equal. Again, but you cannot do such comparisons for everything. Even if you could do it for some parameter, it doesn't mean that you can do it for this parameter for any two objects. So here, even though the word is same, since because this object is involved, whose comparison with this object is intimately connected to quantitative, uh, the quantitative is involved in this comparison. So um, even though we are talking about same areas, the result is quantitative because the object involved is quantitative. The object area of this is already quantitative, and that's why we can do things like that. And there are many similar results, probably infinity. I mean, for different things, not only areas that behave that way, of course. So here we already see that numbers actually produce entirely um, it's called parallel structures to non-number Euclidean geometry. It is structures of existence that simply doesn't have to do anything with the uh, original structures. That is, for example, the structure of area for such objects. But are indeed, in some sense, but are features of the objects familiar from our setting of geometry to non-number Euclidean geometry. And this is remarkable because we started with no numbers, and then we have now discovered that numbers kind of introduce a new part of a mathematical world entirely, even in geometry. So really some objects are now entirely new world. Alright, that's interesting. Right, but every result that doesn't involve quantitative objects can be done in geometry. Okay, well, that is really interesting. And of course, there's no patents for rigorosity here. It's more like, as I said, motivational video for myself actually. Right, okay. But let's do something interesting. Let's try to do calculus without numbers. What does that even mean? And let's try to find out. Uh, what's that? We'll try to take. This is, by the way, very interesting. Um, yeah. First thing that comes to mind. uh, actually, universe themselves can be given, and this is how we'll define them. Subsequent videos can be given in um, abstract algebraic fashion. Where we do assume the very basic properties that make the objects we define symbol numbers, symbol numbers, in particular real numbers. So actually real numbers themselves can be defined in an absolutely abstract fashion. Abstract algebraic way, where we do assume only three basic properties that make objects we define symbol numbers. This is interesting, right? So our pursuit to do calculus without numbers actually basically, if we want to prohibit ourselves numbers, and actually we would have to prohibit those algebraic properties of reals brought together in one object, because otherwise we would already have reals brought together in one algebraic structure. So by wanting to prohibit real numbers, we are actually going to prohibit a very abstract thing. And then the question arises, what grounds is our prohibition based on? What warrants prohibition of putting together exactly those algebraic properties? Because in geometry without numbers, it was kind of clear what warrants the prohibition. We can have an entirely different way of thinking about objects, right? Maybe it was only by posteriori clear, but it was clear. Those algebraic properties. And here we have to think hard. Why couldn't we do that? Basically, what defines the universe is addition, multiplication. Of course, it's not rigorous definition, but just so that you have imagination of that. So, of course, also that. And one another thing that is rather abstract, but it basically amounts to when we always have smallest thing, and really smallest here is the smallest number. so that no matter how close in our collection to this number we are, we can get even closer. If collection is finite, of course, this number would be just the largest number because we can compare with them, right? This is this sign bigger, but if it is infinite, then we will always have such numbers. So upper boundedness. What exactly would prohibit us to put exactly those properties together? That is a good question. Unlike the nature numbers, we are not doing anything special. Any field in algebraic structure enjoys this. Any field. And a field is a strong algebraic structure, but it is quite general. Okay, well, depends, but it's certainly more general than just real numbers. How we put this stuff. For example, take complex numbers, then we didn't know how such a thing works. And we don't know how to compare complex numbers with each other in a sensible fashion so that any two can be compared to each other. Right? Actually, I would maybe take bigger or equal something. So, so that already kind of makes or field something special because what fields do we recall that do that? Oh, fields, it's just that we have addition and multiplication, right? And as I said, I wouldn't define it previously. What do you call those, right? Addition, multiplication, and the multiplication has to be proper, so we have also to have division, right? So, the things that come to mind like that are those, right? I don't actually know, I think, any other field where we have that. And that works like, again, it is proper, meaning that it is compatible with, well, if have like A, B, also have, um, we also have A plus C, C plus B, and depending on whether C is negative or positive, have AC, uh, BC, AC, BC, uh, F, C was bigger than 0, bigger or equal to, no, bigger than 0, and here if C was smaller than 0. Right, we have that proper thing, and we have that upper boundaries, and that already gives you numbers. But of course, we kind of wondering what prohibits us to put those together. And the intriguing answer is probably nothing. So, what we are actually talking about? So, okay, let's prohibit numbers. By the way, I failed. I failed. That is the thing that has this proper and enjoys those with is already real numbers. That's the thing. That's the amazing stuff. That's already real numbers all such fields are real numbers, so they are all same stuff. Then I think anyone would agree that to define an operation with properties like we saw in our videos, find another operation and define some other stuff in fields, we don't need any notion of number. It's really abstract fashion. It's just a map, right? We had something like Cartesian product of group plus operation maps to group, something, right? Alright, closed operation and things like that. In fields, it has to be proper. But okay, algebraic operations are very abstract. For that, we don't need any numbers. No problem. Then we could just start using and defining from scratch, like reals. From scratch, abstractly. Like reals. Other numbers. For instance, the complex ones. Right? But yeah, and we develop calculus with him. I mean, not necessarily with C, but with some numbers. Would it work? Would it somehow work? And it's an open question to me. I do not necessarily know, because we have this abstract definition of use that is really abstract via operations and their properties, nothing else, no numbers involved in any kind at all. If we can define C in the same fashion, well, that's actually, that's, I don't know, but let's imagine we just have this kind of um, field again, field, and that is multiplication, addition work, but now multiplication is defined like for the complex numbers, right? And yeah, this is interesting because I would have to specify those sets somehow. Actually, that's what I would do. Field defined on quotient being set and maybe sufficiently large. But the thing is, for EOS, we don't even assume that. That's astounding, right? But okay, only sufficiently large for EOS. It's just given
by that. Yeah, otherwise we would have rationals. So, I mean, rationals otherwise would fit. So, that is given sufficiently large is given by upper boundiness. Ah, okay, let's have a way. Yeah, imagine you would have calculus at that, right? You could develop calculus in a way, but it would be a substantial problem. Now, why did I start with complex numbers, not with rationals? Okay, we could develop some kind of calculus in that, but it would be a very disappointing calculus because we could get, that rational numbers, get as close to any real number as it gets. I mean, it could get ever closer, but this number would be left out. It would be not there. And so it would be kind of really disappointing because you would only have your rationals. Actually, I think dividing that abstract fashion would give all these rationals, but here I'm not sure because I'm not sure what were. Okay, I won't talk about abstract stuff. Okay. Um, Maybe not necessarily on rationals, but for example, we take rationals and we develop calculus on them. Then we could develop calculus. Okay, I know why I didn't do rationals, so we prohibited all the numbers, right? Prohibited all the numbers, and C is just an example, maybe also prohibited C. But then, of course, the question arises, what did we actually prohibit? The whole abstract algebra? Or did we prohibit all fields? This question would arise, of course, automatically. And if fields are prohibited, are the structures that contain fields prohibited, like structure with operations? So that would be filled, but not. I mean, it could be defined so that it is also filled. Yeah. Okay. So we would prohibit fields, meaning that we also prohibit everything stronger than fields. So that is suggestion. Prohibit suggestion. Prohibit everything. But yeah, we would have a problem because um, we would have also to prohibit groups. Oh, yeah, prohibit everything like rings, groups, fields. Okay, that would be problematic because that would kind of mean prohibit algebra. Okay, so actually by prohibiting numbers, and that is pretty much that, because okay, um, prohibit that is respectively. Okay, but okay, not sufficiently weak. Do not allow for numbers to rise. So that actually means every field at all is prohibited because it would make z rise. Every field is prohibited. No,
no. Every field with with there's a special notation for that, but we don't use it. If there is and we are not with our use, of course I use numbers. There is if there is not isn't maintained such that 1 plus 1 n times equals 0 is prohibited. Every such ring is prohibited. Every such ring is prohibited. Yes, prohibited. Okay, what about groups? Well, there are also natural numbers, right? This also doesn't give natural numbers, so okay, but not all fields are prohibited. But these fields, such fields for which such exists, are allowed. Okay, because that would certainly not give anything that would give our numbers. Okay, alright, alright. Okay, so define such fields abstractly. And by the way, if we have a field that does that, and we have that there isn't such an n, then we have already always our z, so that wouldn't be allowed. And groups could be allowed, some groups, right? But actually, no, groups couldn't be allowed. Groups couldn't be. No. Okay. I see. Groups could be allowed when having encountered by many elements. Or many elements, but finally many elements. Okay, I'll just really okay, wow. So, and the calculus. So, but how? Without numbers at all.
simple. Yes, operations and just write. I don't know. Plus, for example, or of course, or let's go with K. Okay, so field for a K, we have that here, a this multiplication equal a equal a, right?
Alright, we have just written it like that. We have not written it 4 times. We don't ever think about 4 times. We just think, that looks like that, and so we don't count. We don't ever count. We just define it. So we could have some type of numbers, some weird type of numbers. Alright. And if we are going to prohibit those numbers, we haven't looked yet at those properties, but let's imagine we prohibit those numbers. But if we do that, if even such numbers, if even such numbers are prohibited, in fields are prohibited, field settings are prohibited, groups have countably many elements, perhaps allowed. Mm, well, I'm not sure because even having some uncountably many, I don't know, some kind of by the way, uncountably many means we kind of have an infinity that is larger than n. In some sense, we have more, let's say, natural numbers that would be, for example, r would be in this infinity, let's call it, I don't know, not infinity, but some symbol. So this some kind of all infinity is larger than n, but it's not very formal, just um, perhaps they are allowed. Couldn't we extract? Couldn't we extract n in some way, some reasonable warranted way? And we kind of could, so this becomes a question of
I don't even know for, I don't know of what. Ah, okay, actually, yeah, we kind of could. Hmm. G, mental G, such a book. And I mean, of course, that we use the group operations. Let's say the group operation, we denote it like this. We could kind of define the natures in that way. So actually, what we are saying, and let's think about it more naturally. We are prohibited from ever using any repetitive operation. Otherwise, well, from ever thinking operation is repetitive. Otherwise, we have natures. Okay, so we are prohibited from using foods and drinks if we don't allow such numbers. Mm, actually, okay, that need not be that bad because that could be a number that kind of goes down to, yeah, but even if it goes down to like the neutral element of a group after some time, I mean after some finite time, but we don't know the word finite, we just put it like that, and it goes to this. Even if it does, we still consider repetitive operations and just think of that. If we are allowed to think of that, we would have natures. So it doesn't even matter what kind of repetitive operation, we just can't think of that as repetitive. So we actually can't think of repetition at all. We can see repetition, but we are not allowed to recognize repetition. Okay, that means everything like that is of course prohibited, but of course, as you see, it is just different tracks of thinking. We could, on the other hand, say, well, it is prohibited. We don't think of that. We just do now calculus with that. Okay. Well, let's see. Okay, I should of course mention that what we are not allowed to do is to recognize the repetition as a concept. I should mention that what we are not allowed to do is to recognize repetition as a concept. That is what we are not allowed to do. To like repeat without knowing, without seeing it as a general concept is allowed, of course. Right, and to kind of recognize repetition like the triangles or quadrangles is okay. Okay, well, um, so we could kind of, without recognizing repetition, but I'm wondering if by allowing comparisons like something like okay, we are actually what we are not allowed to do. We are not allowed to think of when I have something like this, I can do this. So it's very subtle. We are not allowed to do many things that involve the possibility of invoking natural numbers when generalized to a concept. We are allowed to think, for example, of that as simply uh, actually no connection to that. Yeah, that's a weird kind of thinking. Okay, wow. But what I actually would like to do would really try to do some calculus, trying to not invoke any concepts that use numbers in any way. So let's just try to translate. Um, what do we have as obligatory part in calculus? We have limits. Let's try to think of a limit as something entirely different. Let's do something simple. I don't know. One. Oh no, let's do something really simple. But oh, remember, we are not allowed to think of that. We want now to think of that in some totally different way. So in usual calculus we would do that, right? But we now don't want to do that. We want to consider this relationship in some totally different way that doesn't involve numbers, doesn't involve any numbers at all in any fashion. How could we do that? Uh, well, we are allowed such fields, but uh, wow, I'm actually not even sure if something like that can always be a field, because you see there's a group with respect to this, it has this in this modular group, and okay, I should not use things that you don't know, but it is like a special kind of group. Wait, maybe I'm mistaken. Yeah, okay, not necessarily, because I was thinking of something, but it is only for this. It is only for this stuff, right? It's only for this stuff, for E, where I don't know how someone who doesn't know about repetitions would write that, probably like that, and that would just be this type of drawing. And they would just understand that under that they understand. Wouldn't that invoke numbers? And anything like that. Um, so that would be that kind of thing. So instead of thinking of numbers, you would just understand in their mind that such drawings are meant but would not be able to make any relationships between them. right? Or at least not those relationships that would have led to numbers. So, of course, it repeats, but mm, would how would they understand what? Mm, okay, of course. I mean, like, but what we also tried, and we would conceive those as separate pictures. So of course, it's given because it's otherwise not available, right? They would conceive those as like separate pictures, like not that I first do that and I do that, but like just separate pictures. That is given, that is given, that is given. All right, and then of course they would probably recognize. They would just write, and they would just write anything, and they would just think, "Well, I'm writing now anything," and they would just write arbitrary stuff, and then they would like look. Oh, actually, I see this drawing. This drawing is that, and then would do their mathematics and would do that, and then they would come to a conclusion. Right, because they would just think, well, um, whatever I do is that, I mean, whatever type of drawing I have, is recognizing that the same type of drawing already meaning, understanding concept of number. I don't think so, because there's no relationship between different ones. It's just no relationship except it's same thing, and same thing in very general sense that you understand this type of drawing, right? Okay, the question would be, my question would be, in such a structure, if we don't have, if we don't have like two operations at all, then our calculus would be um, okay. This is not so loud because we could just think of that as the thinking of that like that. So our calculus would be, if we only have such a group, then it would be something. Oh, let's try to define a limit. Any limit. What would be a limit? Of course, it's not n2. Actually, those creatures could define a limit because, or at least some types of limits, because they could just think of that. Okay, they would not be able to. Actually, they would be able. We would be able to visually conceive limits. Of that type at the very least. And they would be able, for example, if G is equal to the G, right, the neutral element of this group, you could watch the video, what was that, matrix arithmetics, to learn the notion of a group and what the neutral element is. And we would just write, So we would have some elementary limits at least, because we would just realize, well, that actually goes on. And again, we would not think of it as ordered in some way, like they can do it. They would not think about doing it another time at another time, conceptually, but they would just know, if I have such a drawing, then I can not do it another time, but put the thing that is not there. And not there, not in the sense that here was one, here is another one, but in the sense that when I draw this, and I draw this, and I draw this, then here, not there, not there, not there, da da da, but here, okay, oh, we kind of feel numbers. We feel numbers, but we do not realize them as a concept. And then they do that. Or maybe, yeah, I know. They do those like this. And then they don't have numbers at all. They just compare. They just compare, and they just see, well, this is like this. I could do like this. Like, right? The concept of equality, I could do like this. And then what I do, so it's not putting the same another time, doing something another time, it's using equality. Okay, now the question is, wouldn't any such procedure, I don't even know how to formalize it yet, be equivalent to natural numbers? Is any procedure in that we can recognize natural numbers equivalent, perhaps, to possibility to formalize this procedure in such a way that everything that we get out natural numbers logically arises from it too. And it is not yet stated in terms if it is equivalent to defining natural numbers, because we would need to understand what it means to define any such procedure. A procedure in that we can recognize natural numbers. For example, this procedure. Take this, take equal thing, can do that. I actually do not think that in terms of thinking, if I always just do equal thing and do not realize that I'm doing that, and I think that this procedure mentally is really not equivalent to defining rational numbers. If you would think about what is happening here, it's kind of like uh, you take a zero, because I could do it same way, right? I could do it elongating, right? You take a zero, and then they are not necessarily of same size, right? They could be different elongations, but maybe they do same size, equality. So we have one measurement thing, and we compare our things with it. Well, they compare not in sense how many times it fits, but they compare just, I have to draw this. Right. Okay, and if you think about it, then what they are doing is 0 goes to 1, but then this is forgotten, and only 1 is there. And then 1 goes to 2, but then this is forgotten, and only 2 is there. But those are also there, but they are only there as separate things. So I don't think this is equivalent to natural numbers. And because they are not seeing possibility to go like this. We do not know that at all. We can only do one step. And we can only look at that step, and we can't bring two steps together. So we cannot do. Can go to to improvise too. Okay. I think those people, if we conceive that procedure, because you see, we have actually one choice, one step operations are possible or impossible. Step operations, possible or impossible. If we have that, we can't think. So one step operations should be possible. First choice, second choice. Conflation, conflating, I know, composition. Mm, let's see, multiple application of one-step operation. Possible natural numbers here, but we want to prohibit natural numbers, so we have to go with impossible. Okay, and that is, if we think about natural numbers properly, then the natural numbers are just realization that one-step operations can be repeated. So, one-step operations can be repeated. and we immediately natural numbers. There's no way to avoid it then. So basically, world without numbers, um, this world without possibility to think of repetition of similar operation of same operation as operation one operation, namely repetition. Okay, I had repetition as operation of operation as operation on the on a an operation. Okay, so excluding natural numbers basically means that without any analogon of an each single operation instance, single operation instance is unique and unconnected in mind, even if from our perspective same action was carried out. So a world without natural numbers is basically a um, world without him is a world without comparative world without him is a world without um, without comparative memory for more than two distinct uh, iterations because for because if we would have more, then we could have let's say we put this object something, let's call it I, you know, then we put another I, and we can compare them y equality, right? And if we would have more, we could have compared that with that, that with that, and we would have three, right? We would have three of them, and we would realize that it is like that. Then of course we could like, yeah, okay, no, not necessarily. We would just have, we can again, with without not for more, but without comparative memory. Actually, it's simpler. It's even simpler. Without memory of, actually it's exactly that, of any previous iteration, previous, of any, uh, without memory of any, so without memory of iterations of an action. Because you see, the crucial thing is not the number, but the crucial thing is that one time doing something is not connected to another time doing something. So even if it is 3 objects or 4 objects or whatever, this creature cannot connect this seeing for objects to this seeing for objects, right? Cannot connect this seeing for objects to this seeing for objects, or at least there's some bound, some certain bound, because if it could, then it would see this for objects, and then it would put this and see this for objects. Okay, there's not necessarily necessity that it would not suffice, but it's with some restriction of memory, with severe restriction of memory, severe. So it is not necessarily that there's no memory about that at all, but okay, I know. Iterative memory, any instance of iterative memory is fine, but without unrestricted, I mean potential unrestricted iterative memory. Right, iterative memory is the memory of an action based on which one can do another action. And here, this sporadically, they could have any instances of such memory, but the ability to such memory is not given. So from our perspective, it will be iterative memory. From their perspective, it will be just sporadic thing. So no access um, to iterative memory that could be applied without impossibility of application and possibility of application at any moment. Impossibility of application at any moment, unrestricted memory, unrestricted iterative memory. Okay, so we cannot do iterations at all actually. And if we now think of a limit, a limit is all about iterations, right? Because it is the only like sensible thinking of limit is actually if you consider this formal definition, or we didn't have yet formal definition, but if you consider that, it's just that we can take any natural number and look at what happens at this number, and without iteration, without this iterative memory, the this going as far as I want, as far as cannot exist. I mean, in sloped terms, going as far as that is any kind of it's basically any kind of limiting process, because any kind of limiting process is intrinsically based with on iteration. You cannot well, but actually that's an interesting thing. You see, if they are capable of producing something like that, right? Because they are capable of producing something like that. Then if we take a total of what they have there, actually, would they have a notion of a total? Yes, of course, because it's visual. We just look at that and like think, ah, no, this does not exist. No iterative memory. We can only think that this one, according to Hira, when we see it, this has no meaning for him. Has no meaning at all. Okay, so no infinite objects and no iterative objects. No infinite objects, no iterative objects. Okay, well. Okay, this is quite interesting. So what we are left with is a world of thinking in which there are no infinite objects, no iterative objects, no numbers anyway, because
Well, could they come up with finite numbers? Uh, well, okay, I'm not allowed to do this. But come up with finite numbers? Um, I think so. We could have, put there. Okay, we can't count. But we could have, imprinted that visual thing, right? And then, for example, we want to do something like we want to do something like this, and this is how we denote this number, and this is how we denote this number. That for us is 4, for them is that, and what for us is 5, for them is that, and they have just visually imprinted that looks like that. All right, and now we want to compute that, and what they do is well, for example, they just look uh, so look at that, then the gaze goes to that, then the gaze goes to that, then the gaze goes to that, into that, into that, into that, into that, and they for each they just go. Oh, that's the only thing that we know. We know to go like that, and so we do for each here. We do another line, and so we have computed the addition of numbers. Okay, you see, even if we only allow that one step operation, that is the minimal thinking that can be. Why comparison? Because comparison thinking, if we don't have comparison thinking, again, we cannot think. If there is no comparison thinking, we just cannot think. And now we can compare. This looks like this, and here is, but this here looks like this, right? And here is, so we think like geometrically, right? And this, so they can kind of have finite numbers, and we can add them. And we would of course never realize the concept of a natural number, but we can add numbers, and basically we have the successor for any natural number because we just know oh, and so on. I mean, in our world and so on. They could add numbers, and that is basically it. They could add numbers, but they would never realize anything about infiniteness and actually anything about what they are doing. They are going like machines in some way, but we could have the concept of numbers for counting in the sense that when we see through I don't know whatever this animal is. So dinosaurs probably true, but okay, let it be the dinosaur. It's historically inaccurate, I think,
but let it be a dinosaur. And they see a dinosaur and uh, I don't know, a tree. Then we kind of first their gaze focuses on that, and they do that because at each thing on which they focus, for example, you want to count like in quotation marks, but you want to count those dinosaur and this tree, and then we do another one. Okay, yeah, another one you always do like that, and so we kind of know the number visually. We don't know it consciously, but we can know it visually. Right, and when they like do go to other objects like I don't know a stone, another stone, and another stone, and then they do what? Well, they look at that and look at that, and then they look at that and they transfer the gaze of that, but then they see, and they see, there is something, there is nothing. So you see, comparison already, comparison thinking, and that's basically just equal unequal. Already allows for comparative counting and reception of one-step thinking. And resumption of one-step thinking ability. But actually comparison already assumes for one-step thinking ability, but maybe there are more complicated operations in one step involved. So yeah, I mean, operations of our nature, not necessarily more complicated, but of our nature. Right. All right. Okay, so those creatures would never grasp anything beyond comparison. So, and the comparison, visual comparison. Okay, as soon as I have um, iterative thinking, nature numbers, and I mean as a concept. Okay, so nature numbers amount to iterative thinking, and of course we also have that. So it's equivalent. Nature numbers are equivalent to iteration. Oh, of course, who would have doubted that? Um, and iterative thinking is important that it actually means remembering same thing because the memory of what you remember is the memory now about the thing before, and it is memory about that thing that was before, but it is same thing is pictured in mind that was before. Right? Okay. Um, And from that, we know that mathematically we must have all numbers. Okay, that's another way. We can construct unique video numbers fitting abstractly. That is what I will do. And we can go all the way of natural numbers to the top. So I usually adopt the top-down approach, but there can be down-top approach. Okay, yeah, okay, so prohibition of iterative thinking in maths. Results in restriction to purely visual arguments. That is all maths we have since started with first geometric visuals with first visual patterns is entirely based on mm, let's not say on creative thinking, but on concepts implying, because that's not the same, implying, uh, implying possibility of deriving from them. Creative thinking. But I'm writing that down, but simultaneously I think about uh, what about abstract differential geometry? If we define it, well, that is just maybe one example, but I immediately think of that example. If we define it uh, mm, manifolds resembling locally, that is, if we take a local piece of an abstract object called manifold and we look at this local piece, and this piece is usually well, actually not necessarily small, but we take a special piece to make locally algebraic objects. Whatever that means, I don't actually know because I didn't have differential geometry any level rather than disassembling like our some space like Rn, so n coordinate axis. So but then have to exclude um, iteration procedures. But that goes better. That goes even better. Whatever it means. What about resembling purely geometrically? Purely geometrical considerations. Could we perhaps define and show geometry in new, in a new setting based on that. But of course, I don't even know remotely what it would be, because usually differential geometry actually relies on exactly calculus. So what that would be, it would be kind of replacing those concepts by purely geometrical considerations or something. Oh, but just some tricks of thinking. But yeah, it really looks like that a lot. And I mean, we have since started with, with humanity. We see the humanity. Okay, I think now I have motivation, because it looks like the numbers are hidden. The numbers are hidden in the fabric of mathematics, because numbers are actually not numbers as we perceive them. They are the iterative thinking parts of structures. They are literally the iterative thinking parts, and iterative not in the sense that we can give that indices, the steps indices, but iterative really in the sense that we remember the action from the past. Yeah, so action memory. This is about nature numbers and whole numbers is kind of undoing actions, right? It's just undoing the actions we have done. I mean, integers is undoing the actions, and rational numbers is oh, here this analogy with actions doesn't work anymore, of course. Actually, rational numbers are quite interesting from this perspective of actions, because they are now an object derived from iteration, but that is okay. They are based actually on an entirely different concept, but that concept we also should talk because okay, I'll be forced to talk about it. Um, but now just say that this is identification because like if I take that and that, and it's like I have one object, and this mathematical object is just this thing, right? And now I could have three such things, and this is one mathematical object. So the information contained in this object is that those three objects are kind of connected into one, right? Okay, all right. Yeah, and rational numbers are defined in that way. Actually, not from natures, but from integers, of course. And this involves a seemingly entirely different concept, which actually, instead of thinking in iterations, that concept kind of adopts a algebraic kind of thinking and says, well, I don't know, it's not necessarily this type of making one object, but let's say we have something very general, we have a set, and set, n subset of n, and tilde subset of n, then we just define this same object, but it's not necessarily of the same type, but of the same type of sameness, but we haven't gone detail anyway, so let's just say that this is defined to be one object when n is actually a subset of n tilde. Alright, and then you see, if you now like do this thing for everything where it applies, and you think of that like you just do subsets, right? You just do subsets, all possible subsets of in tilde, and you don't say I do that and that and that, and you unite them into one object. You say oh, and here you always like an algebraic structure when you talk about an operation plus that is defined for all, right? So here again, an approach is adopted that is actually possible without iterative thinking, because what you are doing is thinking in the whole. So that's interesting. So rationals are obtained from iterations, from iteration thinking, by connecting it with structure, holistic thinking. And what I mean by that again, well, when we have a group, we have simply defined the operation for all objects. So we think entirely of all objects at once. By connecting it with structural holistic thinking. Okay, they obtain from traditional thinking by connecting it with structural holistic thinking. And this is quite interesting because videos are obtained from rationals. By using joint concept of iteration plus structure of holistic thinking. And this is remarkable. So real numbers are actually like the pinnacle of what human thinking can do actually. Iteration plus structure of holistic thinking. I think all mathematics, whatever there is in mathematics, has this as its root. Of course, in mathematics, to complete mathematics, visual, and visual is we think of a derivation from visual thinking, but like plus visual thinking, and then you get mathematics. Yeah, and trios do iteration, structure of holistic thinking. And when you take visual thinking in addition, then you get maths. So, right, that's great. Now, maybe to finish, recall what trios give. Um, Continuous probability theory, that is non-discrete. Limits in the sense of being closest. Well, being being mm, being able to get infinitely close. Close to something. For all nations. And infinitely close because of all rationals also like that, but it's like visual picture again. Being able to get infinitely close to something. I mean, for rationals that are reasonably approaching something, so filling holes. Let's call it filling holes. So, and concepts derived without joint application of holistic and iterative approach. Right, and that is natural numbers iterative approach, rational numbers from integers as holistic approach. And now we have to fill holes. We have to use both approaches at once. Right. Wow. And basically, the same thing is happening like in two dimensions because wow, like Rio's in two dimensions. Imagine that's a plane. We are filling holes between rationals that are put into a grid, right? This is like Q, 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 Cartesian product, same, you could do Q, Q, Q. So Rios are really filling holes. Of course we would, actually, would we? Yeah, of course we would consider that, but to a certain time. But visually, you know, the trios are like what is missing. When we have it, then it is continue. When we only have rationals, then it is not continue. That's what I mean. And so we can go on. So trios are really filling holes. And in that, we allow for smooth transitions. Allow for smooth transitions. And that for smooth. And this is not only about certain maps, I mean, really calculus. Wow, I mean, it's really generally for smooth and uh, holeless. I don't even know if it's a word, but holeless transition, and that is calculus. All right, so what do we get out of it? How's well? Of course, we get differential equations. But you could consider it as part of calculus, but well, and let's say not quite. Okay, and then actually imagine we wouldn't have Rios. We wouldn't have derived Rios. We wouldn't have come up with this procedure. And what exactly that is, we will discuss in quite some time, but we will discuss it when talking about sequences. Um, I think when talking about sequences, yeah, pretty much. Or maybe when talking about topology of reals, so it's will be after quite a while. Um, Imagine what we would have without Rios. We would really be. I think we would be stuck. So pretty much stuck. Like without Rios, we couldn't even do anything by discrete math. I mean, it's kind of in the word itself. Rios give us, yeah, it's like everything that we have derived, kind of, okay, not necessarily everything. Algebraic stuff is not necessarily connected to Rios directly, but yeah, maybe even everything except for algebra and linear algebra include here, of course, for algebra, discrete math. Um, yeah, I don't actually know if algebra is included in here because I would not include that. Algebra, discrete math, but in algebra, I would not even have. Yeah, algebra we would have. Discrete maths, abstract topology. Kind of abstract structural theories. Drug lattice. Abstract structural theories. And that's like um, discrete number theory. And I don't mean that, I mean without use of methods that are actually very useful number theory. Discrete number theory. And what else? Graph theory. Yeah, so yeah, without rules, our pursuits would be limited to this. And I think I even counted almost all. Oh, uh, uh, geometries without numbers. Geometries without quantities. How could I forget geometry? Okay, geometries without quantities. Okay. Yeah. And actually, that would of course also no physics without reals. Yeah. physics, Lagrangian formalism, no, Hamilton formalism, quantum mechanics, and things like that. I think I kind of, even though it was very inconcrete, because I had to keep it simple, reasonably simple, I think I have now got some motivation to do video numbers, because I kind of realized how involved they are in like in the structural sense, what they give, what they symbolize, what their true meaning is, and the simplicity of their abstract definition is kind of um, striking beauty instead of this being I don't know, some boring stuff. It is their striking beauty that from such simplicity we actually get everything, everything except for purely structural and purely visual theories. Purely structural, purely visual, purely iterative. Number theory would be purely iterative theory without. Basically, number theory would be combinatorics without the calculus, complex calculus, and things like that. Finite combinatorics. Theories. Hey, I think this video served their purpose. And well, I don't know if you find it useful for you. It was just kind of thinking about this and that and that and that and whatever not about how views come about, what they symbolize, what is surrounding them, how we would do without them, and things like that. And numbers also, simply any numbers, and that what numbers are, what they are not, what would be by prohibiting numbers and things like that. Okay, now I stop.